The title of this presentation is Conspicuity of Moving Soldiers. My name is Lex Toet and I'm with TNO in the Netherlands. My co-authors are Jaap Bentema and Sjoerd de Vries. This slide presents an overview of the presentation. First I will argue why it's important to incorporate conspicuity of human targets in soldier combat models. Then I will explain the concept of conspicuity and introduce its associated measurement procedure. Next I will discuss the stimuli, task and experimental design used in the current study. Then I will present the results of 4 experiments, addressing respectively the effects of target motion, viewing distance, camouflage type, and the time of year and day on conspicuity. Finally, I will present the conclusions of this study. The construction and validation of soldier combat models requires data on the conspicuity of camouflage targets in the field, and human targets in particular. So far, this data is lacking. Also, it's currently unknown to what degree luminance, contrast and motion contribute to target conspicuity. As a result, current soldier combat models cannot produce reliable predictions on the outcome of engagements involving human targets. To resolve this issue, we obtained conspicuity measurements for moving camouflaged human targets in the field, both for the unaided eye and retinal viewing, and for different target velocities, viewing distances, luminance, contrasts, camouflage types and registration times. Target conspicuity is operationally defined as the maximum lateral distance between target and eye fixation at which the target can no longer be distinguished. After an initial inspection of the target, the observer shifts his fixation point away from the target until it's no longer detectable, for instance towards this white dot here in the scene. Then, in a staircase-wise manner, the observer shifts fixation towards the target until it's just noticeable again in his peripheral vision. For instance, the position of this white dot in the scene. The observer remembers this critical fixation point from visual landmarks in the scene and measures the angular distance between his critical fixation point and the target location. Each measurement is repeated by starting fixation at the opposite side of the target. For each trial, conspicuity measurements were performed by 2 highly trained observers. Conspicuity thus measured depends on the overall target contrast, taking into account all its individual dimensions, like luminance, texture, motion and color contrast. Conspicuity is large when the target contrast is high, and conspicuity is small when the contrast is low in any of these features. Here we show an example of a target with a very low conspicuity. For thermal viewing, conspicuity was measured in the laboratory from video display, using continuously looped presentations of the recorded scenes. The laboratory setup was dimensioned such that the visual angles corresponded to those in the field. Conspicuity is independent of viewing distance when it is expressed as a distance in the frontal parallel plane through the target. Conspicuity decreases with increasing viewing distance when it is expressed as a visual angle. The target was a person wearing a Dutch army uniform, with either a woodland or a desert camouflage pattern, who was situated before a forest. The person wore black gloves and covered his head with a dark pantycloth to reduce his visual conspicuity. Conspicuity data were collected for 2 types of scenes: a deciduous forest at 80 meters distance served as the near scene, and a coniferous forest at 230 meters served as the far scene. Data were captured in summer and in late winter respectively. Thermal recordings were made with a 320 by 240 pixels FLIR camera with a 24 degrees horizontal viewing angle and a frame rate of 50 Hz. Target visibility is highly dependent on target position due to shading effects. We therefore measured target conspicuity at different locations along the forest. Here we show how target conspicuity is affected by the location of the target in the scene and the type of camouflage. The first example shows a person dressed in woodland camouflage running in the shadows of a deciduous forest. Since the target is not very conspicuous, we indicate its position with a circle. The next example shows that the target is more conspicuous at a position in the sun. The third example shows that the target is also more conspicuous in the shade when dressed in desert camouflage, which obviously had not been designed for this type of environment. However, desert camouflage reduces conspicuity when the target is located in the sun. Here we show a static person dressed in woodland camouflage against a coniferous background. The person blends in nicely with the background and is hard to find. Once the person starts moving, his conspicuity increases significantly. In the first experiment, we tested 3 motion conditions: static, walking and running. In the static condition, the target person stood still, facing the observer. In the motion conditions, the person either walked or ran along the forest. The movement was along a cyclic path to avoid position-dependent shading effects. In the nearby scene conditions, the person walked or ran forward and backward in alternation along the forest edge. In the far scene conditions, the person walked or ran in small circles. The maximum speed during a cycle was estimated to be 1.3 meters per second in the walking and 2.5 meters per second in the running conditions. Conspicuity could be measured reliably because the target displacement was limited to only a few meters and motion was continuous. The results show 2 clear effects. First, conspicuity increases dramatically when the target is in motion, even when the target is in the shade of trees and has therefore low conspicuity. Indeed, the observers complained that they lost track of the target as soon as the person stopped moving, and they had to ask the person to move a little in order to relocate the target. The difference between walking and running is much smaller than the difference between walking and static, suggesting a saturation effect. The effect of speed will be studied in more detail in the next experiment. Secondly, we find a small but consistent effect of target position on conspicuity. Targets in the shade are always less conspicuous than targets in the sun, both in static and in dynamic conditions. Although conspicuity increases monotonically with local luminance contrast, the correlation is only weak. A possible explanation is that local contrast doesn't take into account the effect of shadows. A target may have a high local luminance contrast, but if the luminance of the target and its local background is much lower than the average scene luminance, the eye sensitivity to that contrast will still be low. It's likely that contrast sensitivity scales with the overall scene luminance. We therefore computed the global luminance contrast, defined as the ratio of the local target background luminance difference divided by the average global luminance over the entire forest area. This global contrast measure yields a higher correlation with conspicuity and contrast. We will therefore use the global contrast definition throughout the rest of the study. In the second experiment, we investigated the interaction between motion, luminance, contrast and viewing distance. Luminance contrast was varied over a large range by dressing the person in a dark uniform, a Dutch woodland one, and in a much brighter khaki-colored uniform, the Dutch desert pattern. The target was located at a fixed position in the shade of the trees. Viewing distances were respectively 80, 60 and 40 meters. Again, we find a large effect of motion, but we also find clear effects of viewing distance and the type of camouflage. In static conditions, conspicuity for the desert uniform was a factor of 12.6 larger than for the woodland uniform. This factor was 1.7 for the moving conditions. This is probably a result of differences in luminance contrast. Target luminance was 6 times higher for the desert uniform than for the woodland uniform, resulting in a global contrast of respectively 0.24 and 1.48 for woodland and desert uniform. The desert uniform has obviously not been designed for use in woodland scenes. However, this example serves to demonstrate how ineffective a camouflage pattern can be if its mean luminance doesn't match the mean luminance of the background. The data show only a small difference in conspicuity between running and walking conditions. This observation is in line with literature that claims that conspicuity saturates at a retinal speed of about 0.8 degrees per second. To investigate conspicuity as a function of retinal image speed, we replotted the data from experiment 2. Note that although only 3 velocities were tested, 0, 1.3 and 2.5 meters per second, the variation in viewing distance created more than 3 retinal image velocities. The results show that the data for both camouflage types can be fitted nicely with an exponential function. Both curves saturate at a larger retinal image velocity, at about 0.83 degrees per second for the woodland uniform and about 0.74 degrees per second for the khaki uniform. Thus, may reflect the existence of separate motion channels, one for low speeds and one for high speeds. To conclude, the data clearly show a large influence of luminance contrast on conspicuity and a large effect of retinal target speed. For modeling purposes, it's safe to assume that the speed dependency starts to saturate at a retinal target velocity of about 0.8 degrees per second. The measurements were repeated in winter, after the trees had lost their leaves. The results for summer and winter showed no effect of season, except at target position 1. At location 1, target conspicuity was clearly larger in winter, both in static conditions and in the motion conditions. This increase is probably a result of the absence of leaves in winter, so that the target and its immediate background were no longer in the shade. The effect of motion was also measured for thermal motion sequences that were captured during the field trials at 2 locations: a deciduous forest at a viewing distance of 80 meters and a pine tree forest at a viewing distance of 230 meters. For static images we also tested the effect of season and the differences between day and night. The results show various interesting effects of motion, viewing distance and season. First, in summer, conspicuity was much lower at the 230 meters condition than for the 80 meters condition. In the 230 meters condition, the target background consisted of high contrast tree trunks of pine trees that looked very similar to the target, thus creating more clutter than the green leaves of the deciduous trees at 80 meters. Secondly, a clear effect of motion was found in both daytime summer conditions. Note, the effect of motion appears smaller at 230 meters, but this is due to the fact that 3 times smaller retinal target velocities occur. Thirdly, a clear effect of season is observed. For deciduous forests seen at 80 meters, target conspicuity was roughly 3 times lower in winter than in summer. The reason for this conspicuity reduction is most likely the fact that tree trunks become visible in winter, thus adding clutter. This explanation is supported by the fact that the conspicuity for coniferous trees, for which the tree trunks are visible all year, does not vary across season. Fourthly, the conspicuity of the target seen against the deciduous forest edge at 80 meters increases during the night. In this case, the target contrast probably increased due to the lower background temperature. The result of the measurements of the thermal and visual conspicuity of moving camouflage soldiers in the field leads to the following conclusions. Target motion significantly increases target conspicuity independent of the target contrast. For visual images we find that shading has a significant effect of conspicuity that can be captured by taking both local luminance contrast and global scene luminance into account. Target conspicuity increases with global but not with local luminance contrast. The mean luminance of a camouflage pattern has a large effect on its conspicuity. Target conspicuity saturates as a function of retinal speed at about 0.8 degrees per second. The interaction with luminance contrast is highly nonlinear. Seasonal influences of conspicuity can be large, mainly due to the increase in clutter in winter for a deciduous type of forest. For thermal images we find that the variation in the background temperature due to changes in season or time of day plays an important role in thermal target conspicuity. Not only can the thermal conspicuity increase due to a lower background temperature, for instance during the night, but the target conspicuity can also decrease due to automatic scaling of the temperature range by the display software. And target conspicuity can decrease in winter due to an increased clutter of the tree trunks. This concludes my presentation. Thank you for your attention.